Hello, continuing on with the 2020 Oxford PAT, we were up to question 13. So what we got, consider a set of masses of three different values, Ma, Mb, Mc. Each of the following three combinations have the same total mass. So 2 MAs, so 2A plus 3 MBs plus 3B. So that would be the same as 5 A's and 1 C, which will be the same as 2 A's plus 1 B plus 1 C. Okie dokie. Right, so, well, looking at the first one and the last one, we can see that 2B is equal to C. And then, so what can we then do? We can then say 2B is equal to C. So we're going to have that 3A is going to be equal to B. So that means that well, we've already got them all here. I'm just writing them back in the same format. MB is 3MA and MC. Oh, we want them all in terms of MA, so we have to put them into, I can't write that in terms of B. So MC will be 6MA. No, that was just simultaneous equations, so not much to say about that. Question 14. Find all solutions of the following equation in that range. Right, so we're going to want to change, as usual, the squared one into the thing that isn't squared. So we're going to change the cos squared into 1 minus sine squared. So we'll have 4 minus 4 sine squared theta plus 2 lots of root 3 minus 1 sine theta is equal to 4 minus root 3. So we just need to get this into our standard quadratic format. So 4 sine squared minus 2 root 3 minus 1 sine theta, and then the 4's are cancelling, so we've just got a minus root 3 at the end. That's a bit of a mess, isn't it? It really is. I'm just gonna jump to the formula. What the hell? They're allowing us calculators, so why not? So sine theta is going to be 2 minus square root of, so that's going to be 4 lots of root 3 minus 1 squared. It'll be plus 16 root 3, square root all of that, all over 8. I'm just going to stick that into the calculator, which is going to take me a while. I mean, it's maybe it is one of these ones that will factorize, but well, we'll find out in a minute when I've typed all of this in. God, there's so much of it. So, and it comes out, well, okay, right, so it would have factorized then, because we've got root 3 over 2, or we've got minus a half, right? So this is factorizing. So we've got 2, what would we have on this then? We'd have 2 sine theta plus 1 and 2 sine theta minus root 3. Okay, well, maybe you spotted that. I didn't spot that at that point, the factorizing, but there you go. Doesn't really matter. We got the calculators. So that's quite a factorization to spot, but I suppose some people will. So we need to solve this for what, 0 to 360 degrees. So for the root 3 over 2 one is going to be easy, because that's going to be 60 and 120. 60 degrees, 120 degrees. So minus a half means we're going to have to go, well, we'll have two values again. We have to go 30 degrees back, and then we'll go 30 degrees up from 180, so 210. That'll be our 4 answers. Nice, yeah, a bit of a weird one with that factorising. But hey ho. Right, question 15. So we've got a mass M equipped on its lower side with a massless spring, uncompressed length L0. L0 is not in the picture. Spring constant K. The spring is initially compressed to a length L is less than L0 as shown in the figure. Fine. The ball spring system is either dropped vertically or launched with a horizontal speed V0. Yeah, we got that. Height H0, distance X0 over, from a distance X0 from a wall. Right, so we've got this wall over here, which you almost can miss in the diagram. Let's colour it in a little bit. So that's a wall that we've got there of height HW. The spring remains compressed until it touches the ground. When it touches the ground, the spring is released by some mysterious mechanism expands very quickly back to its uncompressed length L0 and is held fixed at length L0. Right, the bounce is elastic. Excellent. Right, so when the ball is dropped vertically, find the maximum height H max the ball spring system could reach after its bounce in terms of the spring's compression, delta L, and all the other parameters. Right. In an analogy to H0 in the figure, H max should be the vertical distance between the floor and the lower end of the spring after the bounce. Okay, so this is going to be, we need to be thinking about energy here. We've got some GPE, and we've got, well, that's going to take us back to the starting point, isn't it? So that will take us back. If it was just GPE, it would just take us back where we began, wouldn't it? Takes us back to start, because all of the work is going into, it's all the mass. The only mass is just, yeah, because the spring's got no mass, so it's only the ball which has got mass. So, but the expansion of the spring is then going to give us, what was it? They were talking about delta L, weren't they, somewhere? Yeah, L0 minus L is a delta L. So we're going to have a half K delta L squared. That's our elastic potential energy. So that's going to give us extra height. So that is going to be equal to our mg delta H, where we've got this extra bit of height at the end. But we have got a change in what's going on with the spring, haven't we? So we're going up delta H, but yeah, we've come down with a short spring. We've gone back up with a long spring. We're looking at what the mass, what this ball is doing, because it's all in the ball is the mass. But now the bottom is further away by a distance of delta L. So we need to take off a delta L from our final answer. H max is going to be equal to H0 plus delta H, but we need to take off the delta L because of the extension in the spring. So we're going to have H0 plus delta H is K delta L squared over 2mg, and then we need to take off a delta L. Right, that's good. I don't know what they've told us. So they've given us G is 10, but they've also told us to have G in the answer. So I think we're okay leaving it like that, I think. Right, okay, so that's that bit. Part B, find the optimal value for the distance x0 from which the ball would bounce over a wall with maximum value of HW. Right, okay, so we want to get, what are we doing here? So the things is coming down, it's hitting the ground, it's bouncing up. We want to get that at the peak of the second, well, the maximum after whatever the next peak is. So that's going to be our H max we're going to want there, aren't we? That'd be our H max. So unless we got anything to go on with spring lengths, but let's put that in for tentatively at the moment. So find the optimal distance for x0 from which the ball would bounce over a wall with maximum value HW. Right, okay. So we're going to want to have, well, our x, first of all, we know that x0 is going to be v0 multiplied by the time of flight, because that's just horizontal projectiles. So we've got, just wondering, do I want to do this with SUVAT and then have lots of potential confusion over what length the spring is at and what should be, trying to do all that accountancy around the old length of the spring and the new length of the spring and all that? Or should I just do it with energy? I think I'll just do it with energy and just think about the ball and not the rest of it. So let's think of then, for the time down, we're going to have the mgh0. I want to get the velocity when we hit the ground. It's going to be a half mv squared. And we can say that, well, the acceleration times the time of flight is going to be the change in the velocity, because the change in the velocity, which is going from 0 to v, so we've got a change in velocity of v, is the accumulation of the acceleration. So we've got those two equations, so we can say that mgh0 is going to be equal to a half of mg squared t1 squared. Get rid of your m's, get rid of a g on either side. So we got that t1 is going to be 2h0 over g. Right, I mean, that's essentially doing s equals ut plus a half at squared, but just not wanting to use the Suvat formula. Plus, it gets us in the mood for doing exactly the same thing on the way back up. So the time up is going to be we're going to have the energy is now going to be mgh0, because that's what we started with, plus the half k delta L squared, that's our EPE. That is now going into our half mv squared that we're starting with. So once again, we're going to have that our g times t2 is going to be equal to our change in the velocity. That's going to be our delta v. That's going to be this v here is equal to v. So that is going to be what we got. We can get rid of, well, not a lot actually. Right, well, let's get rid of those halves and put a 2 there. So we're going to have 2gh0 plus k delta L squared over m square rooted. Right, so that's given us we need to then divide that by g in order to get t2, but that's okay. So, right, scrolling down a bit more, because we just have to do v0 multiplied by time of flight to get our x0. So x0 is v0 times t1 plus t2, which is v0 times the square root of 2h0 over g plus 1 over g, and then all of this thing in the square root sign here. So 2gh0 k delta L squared over m. And that is that, I think. We'll just double check the question. Find the optimal distance. Yeah, x0 from which a ball would bounce over a wall with maximum height hw, right? So hw hasn't appeared here, but it's kind of neither here nor there what hw is, because all we're doing in this is saying, well, what is the value of v0 that you will need in order to get the peak after the bounce to be at a distance x0. So whether it goes over the wall or not is neither here nor there really for positioning what the peak is. You know, it's going to have the peak at that distance x0, and then it's either going to hit the wall or it's going to go over it. You know, that is, you know, irrespective of what's going on. You know, if you think of, well, we're going to be putting something here, whatever it may be, and we want to get the peak there. Well, there's only going to be one way that you're going to get the peak at that particular distance. What the height of the wall is doesn't make any difference to your calculation of the projectile. So whether we've gone over the wall or whether we've hit into the wall is neither here nor there for our calculation. So that's why HW doesn't appear in the answer, because it just doesn't have anything to do with what we're trying to work out. So yeah, that was I would say that's quite a difficult question. Particularly, I don't know what it would be like. I'm kind of tempted to do B again, not that I'm going to, but do that second part again, but taking a more sort of standard Suvat approach and then trying to keep tabs on the length of the spring just to see if I end up getting into a mess or not, because there's a possibility of losing track of where the bottom of the spring is and whether you've actually cleared the wall or not, which is why I sidestepped it by doing this just straight energy approach, thinking about what the mass is doing. So yeah, because if you're just thinking about time of flight, well, it doesn't make any difference then about where the bottom of the spring is. It's just thinking about flight times and then combining that with your horizontal motion. So yeah, it does get away from, you'll notice that there was nothing to do with the spring really in this part B in the calculations. because it's just built into this part of the elastic potential energy. So yeah, I really like that question. It's a great question, but I think it's a difficult one that would be very easy to get mixed up on. Right, okay, I think I've got time to hopefully sneak in question 16 on this. Oh, this doesn't look too bad. Given that, so we've got f dash of x is that, so f dash of x is minus 2x minus x to the half plus a third. And we've got g dash of x is f of x. Okay, and we want to get g of x, right? So we've just got to do some integrating then. So that means that f of x is going to be equal to minus x squared minus 2/3 of x to the 3 over 2 plus x over 3 plus c. So, okay, we've got that f of 1 is equal to minus 1. So f of 1 is equal to minus 1 minus 2/3 plus a third plus c, and that equals minus 1. So c will be equal to a third. Okay, and now we need to get, so g dash of x is that. So we need to now integrate what we've just got again. So g of x is going to be equal to, so we're integrating it again, minus x cubed over 3 minus, what's that going to be? That would be 4 over 15 x to the 5 over 2 plus x squared over 6 plus x over 3 plus another c, and we got g of 1 is equal to 0. So we got minus a third minus 4/15 plus a 6 plus a third plus c equals 0. So we need to get what c is going to be, which is minus, oh no, c is going to be equal to 4 over 15 minus a sixth, which is going to be equal to 8 over 30 minus 5 over 30, 3 over 30, 1 over 10. So we got g of x is equal to, where's it all, minus x cubed over 3 minus 4 over 15 x to the 5 over 2 plus x squared over 6 plus x over 3 plus a tenth. There you go. So easy question, really, particularly compared to the others. So I'll leave that video there. That was what, 4 questions, whatever it was, but that third one was really quite difficult. The other 3 were quite straightforward, but the question 15 was tough.